All right, welcome. Today we are diving into one of the most powerful tools in all of science and engineering, the Fourier transform. Think of it as a special pair of glasses that lets us see the hidden frequency DNA inside pretty much any signal you can imagine, from a clap of thunder to the data zipping through the internet. Let's get into it. So, here's our game plan. We're going to start by looking at the limits of the tools we already have. Then, we'll take this amazing conceptual leap to invent a new one, finally unveiling the transform itself. And then, the really fun part, we'll see how it gives engineers mathematical superpowers and a direct look into the physics of energy. Okay, first things first. To really appreciate what's new here, we've got to understand the old way of doing things. Let's look at the tool we use for signals that just repeat and repeat and repeat and find out exactly where it hits a wall. Now, the Fourier series is honestly an incredible tool. It can take any signal that repeats itself perfectly, like the pure, steady tone from a tuning fork, and break it down into a unique recipe of simple sine and cosine waves. So what does this recipe look like? Well, we call it a line spectrum, and it's basically a set of distinct, separate spikes of frequency. You've got your main frequency, the fundamental, and then a whole series of harmonics at exact integer multiples of that one. It's kind of like a musical chord, but with very specific mathematically defined notes. But here's the catch. The real world isn't always so neat and tidy, is it? I mean, what about a single word that you speak, or a flash of lightning, or even just tapping a key on your keyboard? These are what we call aperiodic signals. They happen once and then they're done. The Fourier series, because it absolutely depends on that repeating period, just can't handle them. It's not built for that. So, this limitation, this problem, it leads to a truly brilliant, kind of mind-bending conceptual leap. It's a what-if question that builds a bridge for us, taking us from the perfect repeating world of the Fourier series to the messy, non-repeating reality we actually live in. Okay, just imagine you have a repeating pulse, a little blip that happens every second. Now, what if you start pushing those blips further and further apart? So now they happen every 10 seconds, then every minute. You're increasing the period, t. Now, what if you just keep pushing them apart, forever? As that period t shoots off towards infinity, what are you left with? Just a single, isolated pulse. You've literally just created a non-repeating signal out of a repeating one. So the big question is, what happens to our frequency recipe when we do that? Well, remember those nice, separate, discrete harmonic lines from our line spectrum? As the period gets longer, they start getting closer and closer and closer together. And as the period becomes infinite, they actually blur into a smooth, continuous curve. We call this a continuous spectrum. We're not talking about specific notes anymore. We're talking about a whole unbroken rainbow of frequencies. Right, so this new continuous spectrum, it needs a new mathematical tool to describe it. And this is where we finally get to meet the star of our show, the Fourier transform. And the really cool part is, this isn't just some random new equation somebody dreamed up. As you can see here, the Fourier transform is the direct, logical result of taking the math of the Fourier series and just pushing its period, t, to the absolute limit. It really is an evolution, not a revolution. And there it is. This integral, this is the engine of the Fourier transform. It takes our non-repeating signal from the time domain, our f of t, and for every single possible frequency v, it spins through and calculates how much of that frequency is hiding inside our signal. The output, f of v, is that continuous frequency spectrum we were just talking about. It's the full DNA sequence. Now, this is absolutely crucial. It's not a one-way street. The Fourier transform takes us from our familiar time domain into this new frequency domain. But, and this is a big but, the inverse transform lets us take that frequency recipe and perfectly rebuild the original time signal. We can travel back and forth between these two worlds whenever we want. Okay, so we've been doing some pretty abstract thinking to get here. You might be wondering, why bother with all this? Well, here's why. Once we're in the frequency domain, problems that are incredibly difficult in the time domain suddenly become almost laughably easy. Okay, now this table, this is where the magic really happens. Look at this. In the frequency domain, really tough calculus operations just turn into simple algebra. Differentiation? That's just multiplication. Integration? That's just division. But the real game changer, the crown jewel, is that last row. Convolution. And that's the whole ballgame right there. In the time domain, if you want to figure out how a circuit or any system responds to an input, you have to use this notoriously messy integral called a convolution. It's a huge pain. But in the frequency domain, you just multiply. That's it. You take the transform of your input, multiply it by the system's own frequency response, and bam, you've got the transform of the output. It is an insane shortcut. All right, for our final section, let's bring this all back down to earth. Because beyond just simplifying the math, the transform gives us a direct line of sight into the real-world tangible physics of energy and something called bandwidth. So how do we make that connection? Well, there's a beautiful rule for it called Parseval's theorem, and it's basically a conservation law. It says that the total energy of a signal is the same no matter how you measure it. You can calculate it by looking at its shape over time, or you can add up all the little bits of energy and its frequency components. You'll get the exact same number. What that really means is that if you take the magnitude of the Fourier transform and square it, you get the signal's energy density. This is the energy recipe. It tells you in joules per hertz exactly how your signal's total energy is spread out across its entire spectrum. And check this out. This is what it looks like in practice. If you take a simple, single rectangular pulse, it turns out that the vast majority of its energy, we're talking about 75%, is packed into a relatively narrow band of low frequencies. Sure, there's energy in the higher frequencies, but you get diminishing returns pretty quickly. And that, right there, is why you hear engineers talking about bandwidth all the time. To send that pulse through a communication system, you don't actually need to preserve every single frequency out to infinity. You just need a channel that's wide enough to capture the band where most of the energy lives. If you get that part, you'll get a faithful copy of your signal on the other end. So let's just wrap this all up. The Fourier transform is our go-to tool for the real world of non-repeating signals. It's born directly from the Fourier series, just by letting its period go to infinity. It gives us an incredible mathematical shortcut, turning hard calculus into simple multiplication. And finally, it gives us a direct physical understanding of a signal's energy recipe and what its bandwidth needs to be. And that leaves us with one last big idea to think about. We've spent this time learning how to read the frequency recipe of any signal, but now that we can do that, what happens when we start to write our own? What can we build when we become chefs of the frequency domain, mixing and matching these frequency ingredients to create entirely new signals, new filters, new technologies? The possibilities really are endless.